We're going to begin this chapter with a review of some trig functions. These are facts that we learned in pre-calculus and in calculus. And I kind of just start with putting out in the next couple of pages here a bunch of stuff that we've learned. And this first page is stuff that really we should know and be familiar with. Maybe we've forgotten it, some of this, and that's okay, but they're kind of the basic definitions up here at the top. The tangent function is just the quotient of sine and cosine. Cotan is the reciprocal of tangent, and so that means it's also equal to cosine over sine. Secant and cosecant are defined to be the reciprocals of the cosine and sine functions, respectively. We've got SOHCAHTOA, which has served us well. That's great for right triangles. We have the Pythagorean identities, and this first one, this is always the one that I memorized. Sine squared plus cosine squared is equal to 1, regardless of what your angle theta is. Now, if you took this equation and you divide through by cosine squared theta, then that gives you that version of the Pythagorean identity. If, on the other hand, you divided through by sine squared theta, it would give you this version of the Pythagorean identity. We've got a bunch of derivatives and integrals. These are ones that we've sort of needed to know probably when we took Calc 1. Here you can see I've indicated the chain rule by using the prime notation instead of du dx. So just a heads up there if you are used to seeing it the other way. We have the derivative of sine is cosine, the derivative of cosine is negative sine, and then over on the other side we've got the integrals. So, the derivative of sine equal to cosine gives us directly this integral formula, right? The integration is just sort of the undoing of a derivative. Likewise, we get that pairing of derivative and integral formulas. And then they're otherwise pretty much straight across, I think. All right. So these are derivatives and integrals we should be familiar with. On the next page, we have some facts that we don't need to memorize. I've got the unit circle here. That's always handy, and we're going to make use of it today. We've got some identities here that are less common, and so I don't, a lot of the times I don't always memorize these identities. But they're useful, so it's good to have this page handy while you're working on some problems. And then we have some more derivative and integral formulas. We've got derivatives of the inverse trig functions here, and then we have some integral formulas. So let's do some examples. We're going to solve this equation. Now, when we're solving trig equations, right, we're trying to find the angle that makes it true. And this usually, it's unwritten here, but implicit in all of these trig equation problems is solve this equation for one go around the circle, right? I'm only going to need to let theta range from 0 to 2 pi radians. And negative root 3 over 2, if we take a look at the unit circle, this is one of those convenient values. The unit circle is so helpful because on these coordinates on the outer ring of the unit circle here, those are the values of cosine and sine for the angle. So the x-coordinate is cosine of the angle, and the y-coordinate is sine of the angle. So if we want to solve the equation, sine theta is equal to negative root 3 over 2, we can use the unit circle, and we can find the y-coordinate equal to negative root 3 over 2. And then it's that corresponding angle that we want to find. So a y-coordinate of negative root 3 over 2 happens here at 4 pi over 3 and at 5 pi over 3. Oops. So that was a pretty simple one in that they just gave us the value of a trig function, and it was a convenient value in that it was a point that's on the unit circle, so we didn't have to use our calculators or anything. This next example, there's a little bit more going on. In fact, there's two things that makes this this equation a little bit harder to solve. One is that there's two different trig functions involved in this one equation, and the second is that there's two different arguments, right? So like that should stick out to us. We want to be able to write it in terms of one argument, and hopefully also in terms of one function. So we need to use an identity to help us out. I'm going to look at, since we have cosine 2 theta here, I'm going to go back and look at the double angle formula for cosine, and there's three versions of that here. Now, in that equation, the other function we have was sine of theta, so in fact, I think what I'm going to use is this version here of the double angle formula for cosine, because it will allow me to write this equation with just sine theta as my trig function. So the left side will become 1 minus 2 sine squared theta equals, and then we have 2 minus 3 sine theta. There's still a bit going on here, but since I have it written in terms of just sine of theta, really we could look at this and see that it's a quadratic equation. It's quadratic if our variable is sine theta. So let's see, I'm going to do some algebra to rearrange this. I'm going to just subtract 1 and add 2 sine squared theta to both sides. And I'm going to rewrite it. So on the left side, right, we've got 0. On the right side, I'm going to start with the squared term. So 2 sine squared theta minus 3 sine theta plus 1. That's equal to 0. And when we have a quadratic that's set equal to 0, that means that we could factor it, if it will factor. And I think this will factor. If it factors, we're going to need a 2 sine theta and a sine theta. The product has to be a positive 1. So I know it's either plus 1 or minus 1 for those last terms. And in the middle, it's a negative 3 sine theta. So it's a negative 1 that'll work. So now I have this product set equal to 0, which means I can set each of the factors equal to 0. And solving each of these is now a bit simpler. So on the left equation here, I'll add 1 and then divide by 2. So we have sine theta equals 1/2. On the other equation, just adding 1 gives us sine theta equals 1. Now both of these equations are in the form of, sine theta equals some value. I'm going to go to the unit circle again and see if I can't find a point where the y-coordinate is equal to 1/2. Positive 1/2. So that happens here and also here. So that gives us the angles pi/6 and 5pi/6. And sine theta equals 1. Well, if the y-coordinate is positive 1, then that means we're at the top of the circle here, and that's the angle pi/2. And those are our solutions. Alright, let's do some calculus. Let's start off with a limit. So we're going to evaluate the limit as x approaches 0 of tan x over sine x. Now, if we let x be 0 right off, tan of 0 is equal to 0, but so is sine of 0. Sine of 0 is equal to 0, so we actually cannot let x be 0 here. What we're going to do is rewrite this. And I'm going to rewrite it first by writing tan as sine over cosine. So I have sine x over cosine x. Now we're dividing this by sine x, so I'm going to write that as times 1 over sine x. Now we can do some canceling. The sine cancels with the sine. Now I can let x approach 0. As x approaches 0, cosine of x approaches cosine of 0, which is 1. And that means this whole limit is 1. Now let's do a derivative. Our function y is 1 minus cosine x over sine x. So this is a quotient, right? We're dividing two things. There's an x in both the top and the bottom, which means I really need to use the quotient rule. So let's take a moment to remember what the quotient rule looks like. The quotient rule says that, let's see, if we call the top function f, 1 minus cosine x, and we call the bottom function g, the quotient rule says that the derivative of f over g is g times f prime minus f times g prime all over g squared. So we have our f and our g, we need the derivatives of those. So if f is 1 minus cosine x, f prime is a positive sine x, because the derivative of cosine is negative sine. And if g is equal to sine x, then g prime is equal to positive cosine x. Now I'm going to plug each of these into the expression here for the quotient rule. So I have sine x times sine x minus f is 1 minus cosine x times g prime is cosine x all over g squared, so that's sine squared x. So this is equal to the derivative. I mean, what we have here is equal to dy dx, but it's definitely not simplified. We want to fix that. So let's do that. We've got in the numerator up top, we start with the sine squared x. Now I'm going to distribute the cosine. I'm going to distribute the cosine, and at the same time, I'm going to distribute this negative. So when we do that, we're going to have a minus cosine x plus cosine squared x. And this is all over sine squared x. I know that we are all really vigilant here, and by the time we make it to Calc 2, we know that we're not allowed to cancel those sine squared x terms because they're not factors, right? The top is not sine squared x times anything. It's just a term up top, not a factor, which means that we cannot cancel. However, we can do some simplifying. You might see it right here the way we have it written. I'm going to do one more step, and that might make it more clear. I'm going to rearrange the terms up top. So I have sine squared x plus cosine squared x minus cosine x all over sine squared x. And if you don't see it yet, I'm going to point it out. Sine squared x plus cosine squared x is equal to 1. So we have 1 minus cosine x all over sine squared x. That's dy dx. It might be worth observing here that the derivative is actually really similar to the original function. Our original function was 1 minus cosine x over sine x, and the only difference in the derivative is that we're squaring that sine function. It's kind of interesting. All right, let's do some integration. So I look at this, and maybe you see the same thing, but the first thing that I kind of notice is that I have this secant squared function, and so I'm thinking maybe I can get it to fit the integral of secant squared. You might review this, or grab this formula from the sheet of formulas, the trig fact sheet, a few pages ago. But the integral of secant squared u du is tan u plus a constant. So if this does fit that form, and it's an if, right? We have to check, right? Integration is, we don't just have like a formula for everything, right? We're going to try to see if we can't make a substitution and see if this integral does fit the form. So if it does fit this form, I think we would have to pick u equal to the square root of x, because that's the argument, right, inside the secant squared function. So let's let u equal the square root of x. I'm going to write that as x to the 1/2, because we know that when we're making a u substitution, the first thing we do after we pick u is we have to find du dx. So du is 1/2 x to the negative 1/2 using the power rule, and then dx. So this is, I'm going to rewrite this now, 1 over 2 x to the 1/2 is the square root of x dx. We have that almost perfectly, right? We are off by this factor of 2. We have a square root of x in the bottom. We need a 2 to go with it. We're allowed to put in a 2 in the bottom as long as we compensate. Now, if we put in a factor of 2 in the bottom, that means we really added a factor of 1/2. And so we're going to put its reciprocal outside, so that needs a factor of 2. And now let's rewrite this with u's. 2 times the integral secant squared u du. Right? Our du is right here. Now we can use the formula for the integral of secant squared, and that is tan u plus a constant. So we've got 2 tan of square root of x plus a constant. Okay, let's try one more. We're going to evaluate this indefinite integral, and we have cosecant plus sine all multiplied by cosecant. And this, when I look at this, there's no form that jumps out at me like there was in the last one. I kind of attached myself to that secant squared and said, oh, maybe it'll fit this form. But there's nothing here that I see that says, oh, here's a form we should try. So I'm going to try algebra first. And we should always remember algebra is one of the most important tools we have in rewriting an integral, right? When we're doing an integral, we're basically trying to get the function, get the integral to reveal its form to us. So I'm going to distribute this factor of cosecant, and then we get cosecant squared x plus sine x cosecant x dx. Now sine x times cosecant x, that's equal to 1 because cosecant is the reciprocal of sine. So we've got cosecant squared x plus 1. And now that we have this written as a sum, we can split it up. So we've got the integral of cosecant squared x plus the integral of 1. The integral of 1 I'm not worried about. We know how to do that. The integral of cosecant squared, well, that's actually really similar to the form we just used in the last one. The integral of secant squared is tangent. The integral of cosecant squared is negative cotangent. So this is negative cotan of x, and then plus the integral of 1 with respect to x is x plus a constant.